Okay, hello everybody and welcome to this class. Thank you for being here on time. So these are the four rules that are used in Conway's Game of Life, and I'm pretty sure all of you are well aware of this. And I don't want to take up too much time explaining this because I want to show you something else today. So last week I invented something on my own, and over the course of the last week, I have been discussing it with a couple of professors here. And today morning, actually, my father was able to write a code for it. So he wrote the code yesterday. He was very much excited about the idea. So today I got a actual computer, so I could actually see it in front of my own eyes. So what was an idea is now something that is clearly visible to me. So I have come up with something called the game of primes. So it's kind of similar to the game of life, but it follows some concepts that are different. So let me quickly tell you what are the rules that are followed in this game and what are the differences with respect to the game of life. So in the game of life, all of you are aware that we have to start the game, right? We have to manually plot a few points and then we have to see how they behave. So it is although it's just a one-time thing, you have to actually do something and you have to decide how the game should go. So based on what you plot, the game will work in a different way. You could probably plot things in a square and nothing will happen. Maybe you could plot them in a spiral, things will happen. You plot them as a circle, some ecosystem will happen. So it's left to chance. The game of primes is you don't have to do anything except watching. Okay, so this game is already happening in the universe and the numbers are already behaving in a certain way. So all we have to do is create an interface which will allow us to observe that. Okay, so how do you start this? So what is your interface? So you start you create a uh, n by n grid. Okay, it could be a square, or let's say it can even be a rectangle. So let me say it's a m by n grid of natural numbers. Okay, you could fill the grid in whichever way you want. I will demonstrate it in a bit, but I just want to explain the rules first. So we start filling the grid and we have numbers from 1 to whatever you want to, and then you just watch. So your job is just to create this grid. So after that the grid will start doing things. If a number, so number has a number has two states. Excited and dormant. So not living or dying, it's just about being excited or dormant. Okay, if a number is surrounded by 3 or more primes, it becomes excited. Okay, so if a number is surrounded by 3 or more primes, it becomes excited. Now as the game goes on and on and on, there will be primes as well as excited states. So let me make it clear and say or excited states. Okay, so in the first round you will not have any excited states, but as we go to the next stage of the situation, there will be excited states. So if a number is surrounded by 3 or more primes or excited states, it could be any combination. It could be 3 excited states, it could be 3 primes, it could be 2 primes and 1 excited state. It becomes excited. Okay, if a number, somebody's microphone is on. Okay, what do you mean by numbers? So Sai asked what's a number. We are creating a grid of natural numbers. So if I create a 3 by 3 grid, it will have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if a number is surrounded by more than 3 excited states or primes, it goes back to becoming dormant. So why are we talking about excited and dormant and not living and dying? Because technically nothing can die or live in this. All the numbers will continue to exist like the way they are. They can just become excited or they can become dormant. Okay, if a dormant number is surrounded by 3 or more primes Okay, so that's already been stated. So if a number, so let's say if a dormant number, I want to make the definitions very clear. Okay. If an excited number is not surrounded by any prime or excited states, it becomes dormant. So these are the rules. This is not technically a rule. So let me get rid of this. Why does this? Okay, so this is Conway's game of life. So let me. Why is this? Okay. Anyway, I'm just trying to make it look. Okay, so these are the rules. You create a grid. So creating the grid is the only thing which is in your control. And then you just watch. So a few things to notice here. The game of life created by Conway doesn't have any bound, meaning you are playing in an infinite domain. You can just, the patterns can keep extending wherever they want to. You could just start off with a small set of dots and they can just go on expanding and it could become a collection of 257,000 dots or something. But in this, you have a grid where you are playing with. So there is only a given area where the things can happen. See, all the reactions that happen, excited, dormant, everything happens in a bounded space. It cannot cross that region. Okay. And the other thing that is in your control is how you fill the grid. You could fill it with numbers from 1 to n. You could fill it with numbers from 2 to n. You could fill it with only odd numbers. If you fill it with only even numbers, then nothing will ever happen because there will never be a situation where a number will be surrounded by 3 or more primes. So it can never come to life. Okay. Now let us see this in action. Okay. So I will first demonstrate what will happen by using a 2 by 2 grid. And I will start with the number 2. Okay, I'll just tell you why. So this is our grid. So we start with 2 and we fill it like this: 2, 3, 4, 5. Now you can ask me, why am I filling it like this and why not 2, 3, 4, 5? Because I want all the numbers, neighbors, to be numbers that are actually close to the numbers. Because if I have a 6 by 6 grid, then if I do 1, 2, 3, 4, 5, 6, I don't want 7 to be here. I want 7 to be below 6. So that the actual numbers on the number line will be the actual neighbors in this grid. Now let's see what happens. 2 is surrounded by 3 and 5, which are 2 primes. So that's it. So nothing will happen to 2 because it's surrounded by only 2 primes. You need at least 3 primes to get excited. 3 is only surrounded by 2 and 5, so nothing will happen to it. 4 is surrounded by 2, 3, and 5. So it is surrounded by 3 primes. So 4 will get life. What about 5? Nothing happens to 5. So let's go to the next situation. So 4 gets life. Now what happens? 2 is now surrounded by 2 primes and an excited state. So it's surrounded by 3 things. 3 is surrounded by 2 primes and an excited state. 4 will not die because it is still surrounded by 2 primes. Remember, for an element to die, it should either be surrounded by more than 3 primes or excited states, or it should be surrounded by nothing. It is still surrounded by 3 primes, so it's continuing to live. And 5 is now surrounded by 2 primes and an excited state, so 5 gets life. So in the next situation, we reach this. And from this point of time, the ecosystem continues to exist in the same way because everybody is surrounded by 3 other things and they just live. They are just never going to have any problem. To die, it should be more than 3. Remember that. So the rules here are a little different from the original Game of Life. So I don't really know all the rules perfectly of the original Game of Life. So these are my own rules, and I've created them in such a way that we want to reach a cycle. So I will come to that in a minute, but I hope you are able to understand what happens here. In the next round, nothing is going to happen. Nobody will die. Nobody will come to life. And this is just how it will continue to exist. Now, suppose we started with 1. What would happen? Okay, now 1 is not a prime. So none of the things here will ever get life because they are never going to be surrounded by 3 primes. So it'll just be like this. That's why I wanted to start with 2. Okay, now let's go to a slightly bigger grid. Let's do a 3 by 3 grid. By the way, big thanks to my father who created this. He wrote this program yesterday. So it so happened that 2 years back he had taken some Java course and he had studied something. And when I told him this idea, he was so excited and he just went and gave me this to actually see it. And I will show this to the professor. So far, how I was showing it to a professor is I would draw it on a blackboard and I would circle it with a colored chalk and see what happens. And the professor is extremely excited about this idea, and I'll tell you in a minute why that is so. Now what happens here? Nothing will happen to 1. 2 will come to life because will 2 come to life? Not really. It's only surrounded by 2 primes. 3, nothing will happen to 3. 4 will come to life because it is surrounded by 3, 2, and 5. 5 will come to life because it is surrounded by 2, 3, and 7. 6 will come to life because it is surrounded by 2, 5, and 7. 7 will just be like that. 8 will be like that, and 9 will also be like that. So only 3 numbers come to life. That is 4, 5, and 6. Okay. Now what happens? Suddenly 1 will come to life. Suddenly 3 will come to life. And suddenly 8 will also come to life. Because now 1 is surrounded by 1 prime and 2 excited states. Remember, once a number becomes excited, it is treated like a prime. So it doesn't really matter. It could either be a prime or an excited state. And 5 will die because now 5 is surrounded by 2 excited states and 3 primes. So it is surrounded by 5 things. And that's too much. To survive, you should just have 3 or lesser than 3. So we reach this situation. But now 5 will get life again because now 5 is surrounded by more than 3 things, right? So 5 gets back life. And we reach this situation. Now, the great thing about this situation is that the corners will never be able to die in this particular grid. Because even in the worst case scenario, the corners will only be surrounded by 3 excited states or primes. So that is not a problem. And they will never die of loneliness because in this grid, each corner has at least 1 prime near it, right? 1 has 5, 3 has 5, 9 has 5, 7 has 5. Now what? 6 gets life, 2 gets life, 4 gets life, 8 gets life, and 5 dies. And this is what happens. Now 5 will get life and all those other people except the corners will die. And we reach a cycle. We reach a cycle. We reached a cycle in a few number of steps. So one of the interesting things to do research on in this particular thing is how many iterations do you need to reach a cycle? And for what type of a grid will you reach a cycle? This talks about the distribution of primes. Because if the prime density is really large, it's very easy for people to get excited and fill the space and reach a cycle. If the prime density is very small, it takes longer and longer for numbers to get excited and become dormant. So as you observe larger and larger grids, it gives you a very good understanding of actually how primes are distributed. Now let's see what happens with 4, a 4 by 4 grid. We are going to start with 1 as it is. This is how it is. And now let's just see when will a cycle happen. My conjecture is that for any grid, a cycle will eventually happen. And that is what I strongly believe in. And for most grids, there will come a situation where everything is excited at some state, or at least all the corners are excited at some state. I want to point out one thing with this particular grid. Here, if 16 gets excited, suppose 16 gets excited, it doesn't stay excited forever. Remember, in the last grid, I told you that if a corner gets excited, it will always be excited. So 1, if it gets excited, it's forever going to be excited because there is 2 next to it. It's a prime. There is 7. 4 will always be excited because there is 3 and 5. 13 will always be excited because of 11. But if 16 gets excited, it might not stay excited because suppose these 3 guys become dormant. 16 becomes dormant because of loneliness, and none of these things are primes. They're all composites. Okay, let's see. Okay. Always remember, if too many things are excited, then suddenly many things become dormant. So now we have so many things that are excited. So most of them will become dormant in the next situation because of overcrowding. And now we reach the situation. Remember, now 16 is not yet excited. 16 will become excited in the next round. and everybody will become dormant except the 3 other corners, because all of them will be overcrowded. So we just have the 4 corners. Now the remaining 3 corners will continue to be excited, but 16 will not be excited anymore because it will be lonely. So we go back to this situation and we reach a cycle. And it's just going to iterate that way. Yes. So Shreyan, do you have a proof for the cycle that there'll always be a cycle?
Yes.
Okay. Please educate us.
Okay. Since there are finite number of primes or finite number of d's, finite number of what we call these, should I call these squares or numbers?
Numbers.
Yeah, since there are finite number of numbers,
Uh-huh.
uh, there are going to be a finite number of ways
Permutations.
in permutations.
Very good.
Okay,
Very good.
so uh, since there are finite number of permutations,
Mhm.
uh, d- you there are it is possible that after, it is impossible that after, like, if now we also know that if something happens and then it goes back to a permutation which had
Mhm.
already happened, if it will come in a cycle.
Correct. It will form a cycle. That's a very good observation.
Okay.
Yes. But there is a small thing that I've added to it. Not only do I want a cycle, but I claim that there will be a situation where all the 4 corners will be excited, or there will be a situation where everything will be excited. So that is there. How do you say that that particular permutation will always happen? Let us see if it will happen in this situation. Thank you so much, Shreyan. So that's a very good observation that you have made, and that was the first observation that was made by the mathematician to whom I showed this. So that's a good observation that you have made. Now let's see if we reached any situation where the corners are excited here. We start off like this. Remember, every pattern that we are seeing here is happening because of the distribution of primes, which technically should not have a pattern. But if this is happening, then it means that there is some hidden pattern which we don't know. Okay, now what happens? All the 4 corners are excited, and here all of them will continue to be excited forever because 21 has a prime with it, 1 has a prime with it, 5 has a prime with it, 25 has a prime with it. So in no situation will you see the 4 corners becoming dormant. So they will always be excited. Okay, looks like we are close to reaching a cycle. I don't know, but might not happen. There are other things that could happen. Notice that the corners are always staying. So now we reach this sort of a situation where there is an alternating of too many excited states and too many dormant states. But we have not yet actually reached a cycle. So the next thing that is required to be written in this code is to keep track of every day. So each of these, I call it as a day. Every day things will change. So by the way, I have to point out one thing here. The change happens instantaneously and it happens to everybody at the same time. It is not dependent change. It's not like first 1 will change, then 2 will change, then 3 will change. So that was what I originally wanted to do, but then I thought it's better to do it this way. So they are not dependent on the change of their neighbor. So it's like one day all of them are like this. At night everybody changes into something based on the previous day, and the next morning everybody has changed into a fresh state. So it's not happening one by one. It's all happening at the same time. So it's more like quantum kind of. So it can get a little tricky if you ask about, because if it is happening one by one, then you can say, oh, so was this dead when this happened, or did it wait for the other person to be dead and then did it become alive? So such things happen. That's why they're all happening instantaneously. Now what happens? Everything is surrounded except for 23. So now everything will die except the corners and 23. But we haven't yet reached a cycle, or have we? Has this thing happened before? It looks a little familiar. Yeah, I think we have reached a cycle. So we will know if we have reached a cycle if we again reach a situation where everything is surrounded except for 23. Yes, there you go. Now Shreyan said that there are only a finite number of permutations, and let's assume that these are, so let's forget about the prime number thing. Let's just say that we are randomly going to make some things excited and then we'll observe something. So let's say there are some permutations. The number of permutations are so many, actually, technically speaking, because you could have one excited state, 2, 3, 4, 5, all the way up to everything being excited. So it's almost like factorial type of situation where you have to add all those cases. But even if that is the situation, why is it that we got into we reached a cycle in about just 10 steps? So that is the thing. How many steps does it take to actually reach a cycle? That could give us a lot of information about the distribution of primes in the grid that we have considered. Now, I will change this entire equation by making something very interesting. I will still go back to a 3 by 3 grid, but instead of using all possible numbers, I will only use odd numbers. So now there is a lot higher chance of us having primes. Now let's see what happens. Does it still reach a cycle? Look what happened. It reached a situation where everything is excited. Okay, there you go. It just happened so fast because now we are having a lot of primes here. We have 3, 5, 7, 11, 13, and 17. We have more than half of the boxes as primes, and we are only dealing with odd numbers. If we dealt with even numbers, I know this is stupid, but just for fun, just to show you what happens, nothing ever happens. There is no way that anybody can come to life. Okay. So this is something very dear to me, and it's not yet officially being, so it's still in the development stages. I have not yet finalized the rules because there was a point of time where I thought that if a number is surrounded by 2 or more, should it get life? Because then we will think about the twin prime conjecture. So suppose there are infinitely many twin primes, then always you will have a situation where something will come to life in any given grid because there exists one twin prime pair in it. But then I thought 2 might be too small a number where things will just start behaving very weirdly. So I thought it's better to make it 3 because now each corner also has 3 neighbors. So I thought 3 is a better way to look at it. Let's see what happens for 4 if we are only dealing with odd numbers. So many things got excited because there are so many.
I have a question.
Yes.
So you told that you are arranging them such that the close numbers are close by, right?
The numbers are close by, yes.
Okay, sir, but so you're using a snake curve in most, but in the
yes.
scenario. But is it okay if we use other curves?
Definitely, you can use other curves. You don't even have to stick with a square. You could do a rectangle. You could do a circle. You could probably fill them in 3-dimensional space. You could probably make a triangle. You could maybe fill them like a spiral, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, like this. Or you could probably fill them outwards. So the creation of the grid is where the actual game happens. So technically you play the game even before the game starts. You decide what the grid should be, and each grid will give you a unique pattern of excited states and a cycle maybe, and you'll be able to observe prime numbers in a very unique way. So here we reached a cycle, if you noticed. So everything became excited, and this is what has happened. So the corners are going to stay that way, and everything is excited. Is there any proposition from anybody to see some special type of situation here? So now it's not in my control to actually change the way the numbers are filled. We have these controls here with us. We can change the increment and we can change the rows and columns. Is there something which anybody specifically wants to observe?
So I have got something.
What a surprise! Yes, what is it?
Okay, sir. Is there such a, like, in the actual game of life, there are many things, like there are things called gliders, right?
What is that? So actually, to be honest with you, I just know the rules of the game of life. I have really not gone too deep into it. Yeah, so you can tell me what it is.
I'll just show you something. Okay. Not sharing. So there's this shape, okay, called a glider. Yeah. So when we start, it keeps on going like this. Okay.
Okay, yeah. So it just keeps extending forever, right? It just keeps
going down.
Okay, yes. I've seen that pattern, yes.
So is there such a stop? So is there such a thing in prime? What?
It cannot happen here because our domain is restricted. So it cannot.
Sir, in the restricted domain, can it happen in the restricted part of the domain?
Okay, so it might not happen here. I'll tell you why. Because all the four corners of the domain all have a chance of being excited at some state or the other. So they all happen. So in the game of life, excited states or life can only happen near your pattern. So you create a pattern, you start with a pattern, life can only happen there. Life will not happen somewhere far away. But here, at the same time, you have excited states happening all over the grid. It doesn't really extend in a way because each of them behaves based on their neighbors around them, and everybody could have primes around them or excited states around them. So it just happens all at once. It's not like we start from here and then something is born and then it extends all the way downwards. No, they all happen at the same time because it's done with natural numbers. There is no situation where as it extends it is creating something or it moves in a certain direction. It cannot happen like that because in all the directions you have things coming to life.
Yes, or in all we still have, but we can. But things over here cause differences in life next to it as well, right?
Yes.
So can't there be a glider type of thing in this game of primes? Can
I
there be? Can there be?
I don't know, Shyam. I should think about it. Can we talk about this after the class? I don't
Yes.
want other people to get bored. Okay, thank you so much. Yes. Okay, so here you can see that if I make the increment as 8, we are not able to start the game at all because we only have 1, 2 primes. We just have 2 primes in our grid. So I have a wild question which technically should not have an answer, but it is just something that I'm thinking about. Hypothetically, this is a hypothetical of a hypothetical thing, so it's very difficult to think about it. But suppose I have this grid of numbers which has infinite numbers in it. This is very difficult to think about, but just assume that I have this grid where I have infinite rows and infinite columns. What will actually happen? Why do I say this is a hypothetical of a hypothetical? Because the game is defined for a grid which is finite. And the moment you say it is infinite, you don't really know what are the neighbors. Because if I say that there are infinite rows and infinite columns, then how do we even reach the second row? Because you just go on filling all the way here. You can never really start your second row. But I'm saying that suppose you assume such a thing, what really happens? Because there are infinite primes, so they will
Sir,
have. Yes,
that is
Shreya.
a Hilbert curve, right?
What is that?
It's a look. Can I? Okay. Okay. Or we can also use that. Okay, we can. Okay, 1 second.
Okay.
I don't have. I okay. I'm not. I'm pausing this so that I can draw pictures on this. Okay.
Uh,
So, so first we go like this. Okay.
Shreyan, can we do this after the class? Because this class is being recorded. So
Huh,
I don't
huh.
want. Can we please talk after the class? Is that okay?
Yes. Yes.
Thank you. Okay.
Okay. How do I remove this thing? Yes. Okay. Okay. Yes. Yes, sir. Sir, are you? Yeah. Continue.
Can you please? Okay. Thank you. Okay. So what actually happens when we think of such a situation? Or let me make it slightly more easier to imagine. Suppose there are only 10 rows, but there are infinite columns. So the columns are going to go forever. Then what will happen? Let's try for a rectangle. Let me just show you a rectangle and let's see if there is still going to be a cycle very soon. And let me just do the normal increment by 1. This is my rectangle. Now, why should this, what is different with this particular pattern when we compare it to a square? A square will always have a center, and that center will always come to life when everything around it
Raghav,
is.
we can't see your screen. We can see you.
Okay, just a second. Oh, sorry. So I think. Okay, just a second. Okay, is it good now?
Yes.
Thank you. Sorry, I didn't really do anything. I just made this rectangle. I've not yet started it. So what is different about this? There's no real center here. So you cannot say that something will. I mean, you have these type of guys here which are surrounded by four, this type of guy, but there's no real center. So let's see if that changes anything. Okay. So there is a little bit of less of a symmetrical feel to it because the number of rows and columns are not the same. So it's like happening in two halves. You have something happening on this side and something happening on that side, and they have to actually merge at some point of time. So you get this sort of a symmetrical pattern. It's a little different from the square. You get two things which are, so now both of them will get life and the ones in the middle will go away. And then you reach a cycle like this. So the other observation that I'm making is whenever it's a symmetric thing, does it really mean that we are close to reaching a cycle? Because this is a symmetric pattern. This is a symmetric pattern. We have reached a cycle. So a lot of things. So there are so many different things that you can do with respect to creating the grid, right from the way you fill the numbers with from that you can also decide the gap between the numbers, and then you can also decide the shape of the grid. It could be a two dimension. When we go to three dimensions, then it gets a little complicated. So I was thinking about the game of life in three dimensions, and actually I got triggered when I saw the swimming pool in Raising a Mathematician. Near the inauguration hall, there's a swimming pool, and there are small squares inside the swimming pool which are colored in dark blue, light blue, and purple or something like that. So that kind of triggered me to think about it. And then I thought, what will happen if the game of life is in 3D? Or can you add time as the fourth dimension to the game of life, where you say that something can be reborn in the game of life, not here. Here there is no such concept, but in the game of life, you can make something become born again after 10 iterations or something like that. So what happens here if you do 3D is a square or a number. So first of all, it's very difficult how you will fill it, but suppose you actually come up with a way to fill it. It will not be surrounded by 8 neighbors, but it will have, so it will be like a cube. So it will have 1, 2, 3, 4, 5, 6, 7, 8. And then above it, so there will be, I think, will it be 15 neighbors? How many neighbors will it have if it's 3D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and above it, right? So 9 above it, 9 below it, and 8 around it. So it will be actually 26. Yeah, thank you, Shreyan. So we'll have 26 neighbors, and that will, then we have to come up with a whole new set of rules. How many should be prime or excited for it to get anyway, that's too difficult. So let's just think about this. Let's look at a 2 by 3 rectangle. So this is the last thing that I want to show you guys, and after that we can stop for today. 2 by 3 rectangle. Does it really ever start? It will, because 4 will get life. Other than that, now you know from the 2 by 3, we know from the 2 by 2 that we first saw that these 3 will also get life. After this, what happens? It just stays like that. So 1 and 6 are completely inconsequential in this particular situation, because they will never get a chance to be excited. Each of them is only surrounded by 3 neighbors, but one of them is 1. So nothing can ever happen to 6. And 1 is also surrounded by a composite number which can never be excited because of 1 not being a prime. So they have some sort of a paradox going on there, and none of them will ever come to life. And this is just how the ecosystem will continue to survive forever. It'll just be like that. Nothing will change. Okay. So that on that note, I want to finish my demonstration of this, and I will stop sharing my screen. I will still stay for some time, and I will answer your questions. And I am thankful to all of you for patiently bearing with this, although you might have gotten so many ideas on the way. So thank you so much, but I'll stay for some questions.